All right, let's dive into this. Molten salt reactors, MSRs. We've got a whole bunch of sources on nuclear energy to go through. Breeder reactors, thorium fuel cycles, and of course, molten salt tech itself.
Sounds like a pretty dense mix.
It is. But that's what we're here for, right?
Yeah.
By the end of this, we want everyone to really get how these reactors work, what makes them so special, and what kind of hurdles they still got to clear. No easy feat.
Definitely not. Complex stuff for sure.
Yeah. But super interesting. Okay, so first off, for those not in the know, what exactly are molten salts? Break it down for us.
Molten salts. It's kind of like it sounds, they're salts, but they're liquid.
Okay, I think we got that part.
But there's a catch. They only become liquid at pretty high temperatures. Like, think of table salt. Good old NaCl.
Yeah, I'm with you.
Solid as a rock at room temperature. But crank up the heat to 801 degrees Celsius. Boom. Melts into this liquid made up of ions.
Okay, so that's molten salt in a nutshell. But we're not here to talk about seasoning our food, right?
Exactly. Molten salts have all sorts of uses in different industries. But today we're diving into their role in nuclear reactors.
Now we're talking. And speaking of nuclear reactors, one of the sources you sent was about breeder reactors. That whole concept of breeding fuel kind of blew my mind. How is that even possible?
Well, it's all about maximizing efficiency. Breeder reactors, they're designed to produce more fuel than they actually consume. Pretty wild, huh?
Yeah, almost sounds like alchemy or something.
It's not magic, though, I promise.
Yeah.
The trick is they have this blanket of uranium-238 around the core. It's not fissile on its own. But when it absorbs neutrons from the fission process, it transforms, turns into plutonium-239, and that is fissile.
So you're basically getting a fuel bonus, creating more as you go. Incredible.
It's a pretty neat trick. Boosts the overall fuel efficiency of the reactor big time.
Now, the article also mentioned something called a fast molten salt reactor. What's so fast about it?
Fast refers to the neutron speed. These reactors, they use heavier metal chlorides in the molten salt mix instead of the lighter fluorides. And these heavier chlorides, they don't slow down the neutrons as much, so the reactor keeps a fast neutron spectrum, which is key for efficient breeding.
Gotcha. So faster neutrons, more fuel. There was also mention of the molten salt reactor experiment, the MSRE. They used a graphite core, right?
Yep, that's right. The MSRE was a proposed fast reactor design, and that graphite core, it helped create that fast neutron environment, really push things along.
So water is out of the question for these fast reactors, then?
Water's a great moderator in most reactors, but here, not so much. It slows down those neutrons too much, which messes with the whole breeding thing.
Makes sense. Although I think I read somewhere that they've been looking into ways to use water. Something about reduced moderation water reactors and supercritical water reactors. Sounds pretty intense.
There's definitely been some theoretical work on those concepts, but it's all very early stage. A lot of engineering challenges to overcome before they become practical.
Right. Okay, moving on. Another source you shared was about the thorium fuel cycle. This one was super interesting to me. So, thorium. How does it work as a fuel? What are the advantages over the usual uranium-plutonium stuff?
All right, so the thorium fuel cycle, it's all about thorium-232. When it gets bombarded with neutrons, it transforms into uranium-233, which, as we know, is fissile.
Gotcha. So, still end up with uranium. But what's the benefit of going the thorium route?
Well, there are a couple of big ones. First, you get way less transuranic waste. That's the really nasty, long-lived radioactive stuff. Less of that is a huge win. Second, thorium itself is much more abundant than uranium. It's literally everywhere.
So less waste, more readily available fuel source. Sounds like a win-win to me. And there was something about thorium dioxide being better than uranium dioxide as a fuel. What's the deal with that?
Thorium dioxide, THO2, it's just a better performer all around. Higher melting point, greater thermal conductivity, and it's way more chemically stable. That means better reactor performance, safer operation, and it's easier to store long term.
Okay, so thorium dioxide is the MVP of fuels, it seems. Now let's connect this back to the whole molten salt thing. I know the Wikipedia article on molten salt reactors mentioned FLiBe, this mixture of lithium fluoride and beryllium fluoride. Why is that the chosen one for these reactors?
Oh, FLiBe is pretty special for a few reasons. Lithium and beryllium, they're both excellent neutron moderators. They slow down the neutrons just the right amount, so fission happens more efficiently.
Makes sense. What else?
Well, FLiBe is what we call a eutectic salt. It melts at a lower temperature than either lithium fluoride or beryllium fluoride alone. That's super important. You need it to stay liquid inside the reactor.
Right, of course. And I remember something about beryllium having this neutron doubling property. Does that come into play here?
Absolutely. Beryllium is a bit of a neutron multiplier. It actually helps create more neutrons in the reactor. which boosts the whole chain reaction, makes things even more efficient.
Well, FLAB is like the overachiever of the molten salt world. So you basically just toss some uranium tetrafluoride, UF4, into the mix, and you're good to go.
UF4 is the most common addition, but researchers have also been playing around with thorium and plutonium fluorides too, seeing how they perform in the mix.
Always good experiment, right? See what works best. All right, so far so good. I think we've got a decent handle on the basics of molten salts and these different reactor designs.
We're just getting started, but yeah, I think that's a pretty solid foundation.
Perfect. All right, so we've talked a lot about the nuts and bolts of these MSRs. Molten salts, breeder reactors, thorium fuel cycles, the whole shebang. But let's get to the good stuff. What makes these things so special? You mentioned earlier that one of the big pluses is inherent safety. Can you unpack that a bit? What makes them safer than your average nuclear reactor?
Yeah, safety is a big one with MSRs. One key thing is they operate at much lower pressure.
Lower pressure, how so?
Well, unlike traditional reactors that use water as a coolant, which has to be kept under high pressure to stay liquid at those operating temperatures, MSRs, they can just chill. The molten salt has a much higher boiling point, so you don't need all that pressure.
So less risk of things, going boom.
Exactly. Think of it like a pressure cooker versus a regular pot. Pressure cooker, all that steam builds up. If the seal failed, it's not pretty. Regular pot, steam just escapes naturally. Much less dramatic.
Okay, that makes sense. And what about that negative temperature coefficient thing? I remember reading about that. How does that play into safety?
The negative temperature coefficient, that's another biggie. It basically means as the reactor core heats up, the nuclear reaction rate actually goes down.
It's like a self-correcting system.
Exactly, like a built-in braking system.
Uh-huh.
Things get too hot, the reactor automatically slows down, prevents a runaway reaction.
So multiple layers of safety built right into the design? That's impressive. Now, let's shift gears a bit. We've been talking a lot about electricity generation, but are there other applications for this technology?
Oh yeah, MSRs have potential way beyond just making electricity. They're high operating temperatures that opens up a whole world of possibilities.
Like what?
Well, think about process heat applications. Things like producing hydrogen fuel, desalination. Huge potential there.
That's wild. So we could be using MSRs to power everything from cars to clean water plants. The future's looking pretty bright, especially if we factor in all those thorium fuel cycle benefits we talked about. Less waste, more sustainable fuel source.
Absolutely. MSRs, especially those running on thorium, they could be real game changers for a sustainable energy future. No doubt about it.
Okay, but let's not get carried away. We did talk about some pretty hefty challenges earlier. Corrosion, fuel reprocessing, we got to solve those before MSRs can truly take over, right?
For sure, those challenges are real. Corrosion, that's a tough one. Molten salts can be pretty nasty on materials. Finding stuff that can handle that kind of heat and corrosive environment, that's a big area of research.
And fuel reprocessing, not exactly a walk in the park either.
Definitely not. It's a complex process. But hey, that's what engineers are for, right? Solving tough problems.
Well, I'm glad they're on the case. But all this research and development, it's going to take time, right? We're not talking about a quick fix here.
You got it. MSRs, they're a long-term play. We need to be patient and invest in the research. It'll pay off in the end, but it's not going to happen overnight.
Right. Patience. Got it. Now, what about the economic side of things? How do MSRs stack up against traditional reactors cost-wise?
Well, on the one hand, they have the potential to be more competitive in the long run. Higher efficiency, lower operating costs, less waste to deal with. And thorium being so abundant could mean cheaper fuel costs, too.
Sounds promising. But what about the upfront costs? Building these things can't be cheap.
That's the tricky part. Right now, the initial investment for an MSR is higher than for a conventional reactor. Why? Well, the tech is still fairly new. The supply chains for all the specialized materials and components aren't quite there yet, so costs are higher.
A classic chicken and egg problem. We need more investment to bring the costs down. But who's going to invest if it's not cost effective?
It's a challenge for sure. That's where governments and public-private partnerships come in. They can help bridge that gap, provide the funding and support to really get MSR technology off the ground.
So are we saying we need to pour more money into MSR research?
Yeah.
Especially given the urgency of climate change and all that?
I think there's a strong case to be made for increasing investment. The potential rewards are huge. Clean energy, reduced emissions, improved safety, and less risk of nuclear proliferation. But we also need to be smart about it. Make sure the research is done responsibly and safely.
Speaking of proliferation, I remember one of the sources mentioning that MSRs could actually help reduce that risk. How does that work?
It comes down to the design of the reactor and the thorium fuel cycle. With MSRs, the fuel is constantly being reprocessed, so it's much harder to divert enough material to make a weapon. Plus, the thorium cycle produces way less plutonium, which is a key ingredient in nukes.
So less plutonium, less risk. That's definitely a plus. All right, this has been a fascinating deep dive so far. We've learned a lot about the technical side of MSRs, their potential benefits, and the challenges we still need to tackle. Anything else you want to add before we wrap things up?
I think it's important to remember that energy, it's a complex issue. There's no single magic bullet solution. MSRs, they're a very promising technology. They could play a big role in a cleaner, more sustainable future. But we need to approach this with a balanced perspective, acknowledge both the good and the bad, and keep the conversation going.
As we're talking about all this, MSRs, the potential, the challenges, it kind of takes me back to the early days of nuclear power in general. All that hope and excitement about this new tech that could provide clean, abundant energy. You see any parallels there between that era and where we are now with MSRs?
Yeah, I see what you mean. There's definitely a similar vibe, that sense of optimism. But also, let's be real, a lot of the same concerns too. Safety, waste, the whole what if it gets into the wrong hands thing.
Right, right. History repeating itself in a way. But hey, maybe this time we can learn from the past, right? Take those lessons and apply them to MSR development. Make sure things go smoother this time around.
Absolutely. Understanding where we've been can definitely help us chart a better course for the future. Speaking of which, we've covered a lot of ground here. The tech behind MSRs, the potential upsides, the roadblocks. But let's zoom out for a second. What are the key takeaways here? What do you really want our listeners to remember about molten salt reactors?
Yeah, good point. Let's give everyone a little cheat sheet to walk away with.
Okay, so first and foremost, MSRs, they're a whole different ballgame compared to your typical nuclear reactor. We're not just talking minor tweaks here. This is a fundamental shift in technology. And with that comes a whole new set of advantages. Inherent safety, high efficiency, less waste, and the ability to use thorium as a fuel. Those are all big deals.
Big deals indeed. Especially as we're trying to figure out how to power the planet without, destroying it in the process. But let's not sugarcoat things either. MSRs are still a work in progress. Lots of kinks to iron out before they're ready for prime time.
Totally agree. There's a reason we're still talking about research and development. This isn't something we can just flip a switch on and roll out tomorrow. It's going to take time, investment, and a whole lot of ingenuity to solve those remaining challenges.
Patience is a virtue, right?
Big time. And while we're being patient, it's super important to keep a level head. Acknowledge the potential, but don't shy away from the challenges either. Honest and open conversations, that's how we make sure this technology develops responsibly.
Couldn't have said it better myself. Informed decisions require knowing the whole story, the good, the bad, and everything in between. Well, folks, that's a wrap on our deep dive into the world of molten salt reactors. Hopefully you've all learned a thing or two, maybe even gotten a little bit excited about the future of nuclear power. It certainly got me thinking, and that's what it's all about, right? Sparking curiosity, keeping the conversation going. So, until next time, keep those brains buzzing.